The overall aim of this procedure is to compensate for the degrading effects of atmospheric turbulence on astronomical imaging. As light waves pass through the atmosphere, they are distorted. The compensation described here begins by focusing a high-power laser beam in the direction of an astronomical object to create a bright, artificial reference source. Next, the shape of the returning laser light wave is measured with a wavefront sensor. Next, a command is sent to the deformable mirror in the optical system to correct the shape of all incoming light waves, including those from astronomical objects. Ultimately, the adaptive optics correction recovers diffraction-limited images with an angular resolution of around 0.1 arc-seconds at visible wavelengths on a 1.5 meter telescope.
One main advantage of this technique over existing methods, like those performed at large telescope facilities, is that our Robo-AO system operates at visible wavelengths.
The other main advantage is that it operates in a very efficient, fully robotic, automated mode.
Using these capabilities, we will search for close companions to nearby stars, most importantly those known to host exoplanets. We will perform precision measurements of the motions of stars in nearby stellar clusters, and we will search for and obtain images of transient events such as supernovae.
A key use for this system is in support of transiting planet surveys like NASA's Kepler mission. If Kepler sees a transiting planet candidate, it might be a real planet, or it might be an astrophysical false positive. So Robo-AO looks at these systems to try to rule out false positive scenarios by looking for blended stars close by. And this is a key step in confirming that the thousands of Kepler candidates are actually planets.
In addition to surveys that require an extremely large number of targets, the robotic